Talk about using the sine and cosine functions. So we're going to do a few different things with these. First of all, now that we know about these parent functions, first problem is sketch a graph of f of x equals 3 times pi over 6 times the quantity x minus 0.5, all minus 5. Okay, this is just a bunch of transformations to our parent function. So let's start with the x, like we always would. The first thing that happens to that is we subtract a 0.5. That then gets multiplied by pi over 6. That then ends up inside of the sine function, which we then multiply by 3 and subtract 5. So if we want to graph this, this is a transformation of the sine function. We know some things about the sine function. In particular, we know points that are on the sine function. And so we're going to grab those quadrantal angles, the 0, pi over 2, pi, 3 pi over 2, and 2 pi. And we know that the sine, I like to remember it as this is a middle, high, middle, low, middle. So this one, the y coordinate at the angle of 0 is 0. Then it climbs up to the 1, drops back down to the 0, drops down to the -1, comes back up to the 0. And so now if we just do what the arrows say to do here, this first arrow to the right says multiply everything by 3. So I get a 0, 3, 0, -3, 0, and then subtract 5 from everything. That gives me a -5, -2, -5, -8, and -5. And on this other side, I'm going to need some arrows heading back the other direction. So this is going to be, instead of multiplying by pi over 6, I'm going to multiply by 6 over pi, and then add 0.5. So when we do that, 0 times 6 over pi gives me a 0. I'm going to squeeze that in there. 6 over pi times pi over 2, the pi's would cancel. 6 divided by 2 makes a 3. 6 over pi times pi gives me 6. 3 pi over 2 times 6 over pi. My pi's cancel. I get 18 divided by 2, which is a 9. And this is going to give me a 12. And so this is going to give me a 0.5, a 3.5, a 6.5, a 9.5, and a 12.5. So as I'm graphing this, I'm going to start with my marks on the x-axis. And my first one, I'm going to say that's where 0.5 is. And then I'm going to come out here, reach out this direction a little bit, and say that's where 12.5 is. And then I'm going to break this gap roughly in half. That's where the 6.5 is going to be. And then each of those halves I will break in half. That's where my 3.5 and my 12.5 are. And now we'll plot some points. At the 0.5, I should be at -5. So I need to mark my other axis here. I'll say that that is -2. And I'll make this the -8, which means halfway between them is the -5. And so I have a point at 0.5 comma -5. And then at 3.5 comma -2, so that's my next one. This is up here at this high point. It's going to come back to the -5 there. At my next one, it's going to drop down to the -8. And then it's going to be back to the -2 right there. So this section of the graph, I now draw my S-shaped curve through there. Okay. Looks like it got a little bit wonky on there because I didn't plan to make that curve back the other direction because I know it's going to continue on this way. Okay. And I could draw more of it back the other direction, try to make a gap about this same size here. So with that size of gap, if I bring that back to this direction, say, okay, this coming back that direction, and if I break those things in half, half there, about half there, about half there, and I can continue back to these points. This is when it's going to hit the low one here, be back to the middle about here, a high point around there, back to middle there, and can kind of continue what that would look like if I want more cycles of that. Okay, so that would be how I can use the arrow diagrams to graph that equation. Okay. Let's take a look. I could draw a lot of other information out of there, but these other problems are going to ask for that anyway. So identifying the features of trigonometric functions. The vocabulary that went along with this, we talked about on the parent function notes, period, and amplitude, axis of oscillation, and a phase shift. Okay, so we're going to start this out the same way by making an arrow diagram. So we start with the x, says add a pi over 6, then multiply by 3, and then put that into a cosine, multiply by 12, sign change, and add 14. Okay. So here is our parent function. Here's where the cosine is. So this is where our 0, pi over 2, pi, 3 pi over 2, and 2 pi are going to go in there. The cosine function starts at the high point. So this is the x-coordinate at an angle of rotation of 0 is 1. Angle of rotation of pi over 2, that's pointing straight up. The x-coordinate there is 0. And then it drops to -1, back to 0, and back up. I always think of this as high, middle, low, middle, high. Okay. All right, and now I just do what the arrows, before I jump into what the arrows do, if I remember this gap from here to here, that was where I read the period. So when I've done all my transformations, whatever that new gap from the top to the bottom is, that will be the period. Okay, this gap from here to here is what the amplitude is of the parent function, and so I'll see what that is at the end. My axis of oscillation corresponded to any one of these things that was at a 0 and went above 0 and below 0, equally spaced there. And my phase shift came from this top coordinate right here. So let's do what the arrows say to do. So move over here, it says multiply everything by 12. Change the sign. Add 14. 14. And back to 2, kind of on top of that other graph, that's okay. Coming back this direction, I'm going to need to divide by 3 and then subtract pi over 6. 0 divided by 3 is still 0. This is going to be a pi over 6. This will be a pi over 3. This is 3 pi over 6, which is, I'm going to leave it as 3 pi over 6. And 2 pi over 3, which I'm going to write as 4 pi over 6, because I know my next thing is going to be to subtract pi over 6. So this pi over 3, I'm actually going to make that a 2 pi over 6 and keep that denominator where I want it. So this now is going to be negative pi over 6. Pi over 6 minus pi over 6 is 0. 2 pi over 6 minus pi over 6 is 1 pi over 6. 3 pi over 6 minus 1 pi over 6 is 2 pi over 6, or pi over 3. And 4 pi over 6 minus pi over 6 is 3 pi over 6, or pi over 2. Okay. Which I may actually have wanted to leave that again, interpret that as 3 pi over 6, because I want to see what the gap is between 3 pi over 6 and negative pi over 6. So that is 3 pi over 6 minus negative pi over 6 is a gap of 4 pi over 6 or 2 pi over 3. That is the period. So my period on this function is 3 pi over 6 minus negative pi over 6, which is 4 pi over 6, which reduces to 2 pi over 3. The axis of oscillation, if I wanted to do that, or let's see, my amplitude. Let's go ahead and grab amplitude was the size of this gap right here. This is now where I can read the amplitude. Okay, I'm always going to give it as a positive number. My amplitude is the difference between those. 14 minus 2 is equal to 12. So this has an amplitude of 12. The axis of oscillation, I can follow from this point right here is now right here. So that is my axis of oscillation. I'm going to get this out of the way. This is like the middle line through there. This is an output, so that's a y. The axis of oscillation has an equation of y equals 14. Okay, that's the center line on this graph. And finally, the phase shift, which is going to be right here. So my phase shift is negative pi over 6. Okay. So it says basically this has been moved pi over 6 to the left, and that's where the first, in this case, low point is because of the reflection. So it's going to start at a low point right there and then cycle through. Okay. So actually, the phase shift probably more accurately is to point out where, rather than here, where the first high point of the graph is. And the high point of this graph, because of the reflection, is now when it hits the 26. So that should be a positive pi over 6 as the phase shift. Okay. All right, so on the cosine function, that curve, the shape of the curve, again, that we're looking for is this is the basic shape. And so the phase shift, we're looking where the first time we hit that high point. Okay. On a sine function, we're looking at the first place where we're in the middle but on the way up. Okay. All right. So we certainly would have had enough points in there that we could have sketched the graph of that as well. There's a lot of interconnectedness in the things that we're doing here. All right, modeling oscillating phenomena. Find the equation of the graph that's shown. So we have some choices that we can make here. We're going to try to find places. This seems like a really clear point where that hits there, and this is actually a 1, 2, 3, 4 going up this direction, and this is a 1, 2, 3, 4, 5 going across here. It's a little bit blurry. Okay. But this point is definitely on there, and the next very clear point that we have is this one, which is at 3, 2. Okay. And so we can see, first of all, because of this shape then that I've identified, this is a starting in the middle shape, and so that's clearly a sine interpretation, but it's going down from the middle, so it's a reflected sine. So I'm going to start in here and say what I've got, I'm working off a sine parent function, but then I am also reflecting that right off the bat to get to these points. Okay. So I've done that so far. The period here, I know that the other things that may be happening here My period is, I can read that off right here, the period is 3. Now that's shorter than the normal period, okay? Normally the period is 2 pi, which is like 6.2, so this is somewhere around half of that. We'll have to try to figure that out. But this is a horizontal compression then. So there's a horizontal compression that's going on, and we can probably figure out what that is, because we need to know if the normal period is 2 pi, what do I divide that by in order to get a 3? Okay? Because that's what I want the period to actually be. So if I just do a little cross multiplying here, or I swap the 3 and the x, it tells me that 2 pi over 3 is equal to x. So the thing that I need to divide by is 2 pi over 3, or multiply by 3 over 2 pi. So I'm going to multiply there by 3 over 2 pi. This does start on the 0, so there hasn't been a left to right shift on this. So that should be the end there, and we'll verify that here in a little bit. Okay. The amplitude, if I look, here is the line that goes down the middle. The amplitude here is 2, so that is a vertical stretch. Normally the amplitude is 1, now it's 2, so I'm going to double the amplitude. And the axis of oscillation is usually at 0, and now it's at 2, so it looks like I must have shifted up 2 to make that happen. Now let's test with my points on the parent function. Normally this is my 0, pi over 2, pi, 3 pi over 2, and 2 pi. This goes to 0, 1, 0, -1, and 0, pulling those right off my understanding of the parent function and the unit circle. Sign change on all of those. Multiply them all by 2, and add 2. I did that right. 2 plus 0 is 2. Multiplied everything by 2. All right, 2, 0. Something feels weird that I feel like I did something. 2, 0, 0 plus 2 is 2. 4. No, I'm okay. All right, so this is indicating that I should have outputs of, in order, 2, which I have there, and then 0, and then 2, and then 4, and back at 2. So I like those outputs. Okay. This, if I multiply by 3 over 2 pi, this is still going to be a 0. 3 over 2 pi times pi over 2. The pi's cancel, and I get 3/4. 3 pi over 2 times pi. The pi's are going to cancel. I'm going to get 3/2, or 1.5. 3 pi over 2 times 3 over 2 pi. 3 over 2 pi times 3 pi over 2. The pi's are going to cancel. I'm going to get 9/4, or 2.25. And 3 over 2 pi times 2 pi is just going to be 3. Okay. So, do I have a point at 0, 2? Yes, I do. Do I have a point at what looks like 3/4, 0? That happened back here before the 1. I could believe that. At 1.5, 2. 1.5 is right here, 2. Looks like it's giving me all these points. 3, 2 at the end, so that is all good. And so this set of arrows creates that graph. I wanted an equation, so I'll start with the x there. This is going to say, first of all, multiply by 2 pi over 3. So I'll take my x I'll multiply it by 2 pi over 3. That goes into the sine function, which I change the sign on and multiply by 2, and then add 2, and so this should be the equation of that graph. Okay. If you put that into Desmos and verify that, I'm pretty confident. Okay, now a story. Okay, so we have a Ferris wheel. Everybody remembers Ferris wheels look like this at the fairgrounds, right? They've got kind of some brackets holding these things up, and little baskets on here, people riding around. Okay, and spokes, obviously, some supports on this. So there's my Ferris wheel. It says this one turns around 3 times every minute. Okay, so that's like once every 20 seconds. Okay, so we do 1 turn in 20 seconds. So every 20 seconds this repeats. That's going to be our period. Okay, so that's what we need the period to be. It has a radius of 20 meters. Okay, so from here out to any point on there is 20. The axle sits 12 meters above the ground. So from here to here is 12 meters. Okay. Well, that's going to be a problem, isn't it? Okay. So let's make a little bit of a change here and say the diameter was 20 meters. Okay. So if the diameter is 20 meters, then that means that the radius is 10 meters. Okay. It'll be fixed on your page when you take a look at that. So diameter is 10 meters. The axle sits 12 meters off the ground. Okay. You and whoever are the last couple to get on. So you get on at the bottom, and let's kind of mark out your ride here. Okay. So the Ferris wheel starts at time 0. Okay. You are the height above the ground. Keep track of that over here. At time 0, your height above the ground is 2 meters, right? Because this is 12 meters up this way. This down to here is 10 meters, so that leaves a little 2-meter gap. Okay. At the next easy place to know how high you are is maybe right here. So if this is spinning this direction, at this point, you are going to be 12 meters off the ground, and that's 1/4 of the way around. And if this takes 20 seconds to go all the way around, then that must be after 5 seconds that you are 12 meters off the ground. Okay? And then every 5 seconds, we'll be able to tell where you are. At 10 seconds, you have arrived at the top. This was 12 meters here, another 10 meters there. You're now 22 meters off the ground. And after 15 seconds, you're now back over here, another 12 meters off the ground again. And then after 20 seconds, you're back down to the bottom. Okay? So we know that these points should be on there. At 25 seconds, you're back to 12 meters above the ground. And as long as they let this thing run, we will continue to see that pattern over and over again. So we can see from this that it's starting at a low point and heading up. So this is like the cosine. It's the basic shape of this function is going to be like this that we're looking at, but it's a cosine that's been flipped over. So let's throw a parent function in here of a negative cosine. We'll go ahead and throw the reflection in there right now. Let me pump that up just a little bit. And the points that we know are on this are actually 0, pi over 2, pi, 3 pi over 2. Let me try to line those up a little bit better with what I've got on there. Pi, 3 pi over 2, and 2 pi. And normally the cosine would start at its high point, but this is a negative cosine. So it is at its low point. It's going to climb to the middle, then to the top, come back down to the middle, back down to its low point. Okay. And if we've taken care of the reflection, then there can be at most 2 arrows that we need to do to get over here, and 2 arrows that we need to do to get over here. And we'll take care of any stretches and things first. So the first thing that I look at is my amplitude here. The gap between these numbers is just 1, but the gap between these numbers is 10. So the gap is 10 times as big as it was, so that tells me I should probably multiply by 10. If I do that, I'm going to get a negative 10, a 0, a 10, a 0, and a negative 10. Think about that for a second. Pause the video. Make sure you understand how it is that I knew that I needed to multiply by 10. Okay? Making those gaps match. And now here, how do I change a negative 10 into a 2 in the same way that I change a 0 into a 12 and a 10 to a 22? Well, 0 to 12 looks like I'm adding 12, and if I add 12 everywhere, that makes everything else work. Okay? So over here, let's take a look at the same kind of process. My gap, and I can look at the gap anywhere. It's going to be a little easier maybe if I look at this gap. This is a gap of pi, but this is a gap of 10. So that's 3.14. What do I have to multiply a gap of pi by to get a gap of 10? Okay. Well, I'm going to have to multiply that by 10 divided by pi. So if I multiply by 10 over pi here, see what I get. Get a 0 out of this. Pi's cancel. 10 divided by 2 is 5. 10 over pi times pi is 10. 3 pi over 2 times 10 over pi. The pi's will cancel. I get a 30 divided by 2, which is 15. And this is going to be 20 pi divided by pi, which just simplifies to 20. And it looks like these numbers exactly match these numbers, so I don't even need this last arrow. So if I started with my time here, instead of multiplying by 10 over pi, coming back this direction, I'm going to multiply by pi over 10. And so my equation for the height above the ground after any given time t should start with a t being multiplied by pi over 10. And then I'm going to put a negative cosine around that, which I'm then going to multiply by 10. I didn't leave my space for that. Negative 10 cosine pi over 10 times t and add 12. And so this should be my equation that predicts my height above the ground on this Ferris wheel after it starts. Okay, so this is definitely for only t greater than or equal to 0, and there's probably a reasonable domain at the end. They're not going to let this run forever. Maybe they let it run for 5 minutes or something. That would seem even kind of long. If it runs for 3 minutes, my time here is measured in seconds, and so it's like 180 seconds. So this would do the job for all times between 0 and 180 seconds when they then stop the ride. Okay, that was probably kind of long. Sorry about that, but lots of detail that we needed to get in there.